Okay, YouTube, my last few videos have been looking at sequences of numbers. In this video, we're going to look at a very particular type of sequence that we refer to as an arithmetic sequence. And it's just an example of a really, I guess what we call a well-behaved sequence of numbers. So taking a look at an example of some data that would illustrate some arithmetic growth, in this case growth. Let's take a look here. It says the bar graph and the figure over here shows how much Americans spent on their pets, rounded to the nearest $1 billion, each year from 2001 to 2007. So we can see as time is flowing here from that set of years, we can see how much it's going up by every year. And I guess what I want to point out is this. It says the graph illustrates that each year spending increased by $2 billion. So this sequence of annual spending, this sequence of numbers here, you can see that it's always increasing by a difference of 2 right there. And that difference right there is, I guess, the key to what makes something arithmetic. So if we say that this difference between our terms is constant, or a common difference between the terms, then it's an arithmetic sequence. So we define an arithmetic sequence simply by saying that yes, an arithmetic sequence is a sequence in which each term after the first differs from the preceding term by a constant amount. And that constant amount, we say the difference between consecutive terms is called the common difference of the sequence. So that common difference is what we're going to kind of focus on at the beginning here. How do you recognize something's arithmetic? You look for a common difference. So this common difference here, one thing I guess I do want to write here is the common difference is given by the letter D, and we'll see this a lot. But that common difference is something we want to find here. So for instance, in this first sequence of numbers here, I recognize that it's going up by 4 every time. And so we would say that the difference here is 4, but the way we obtain this is you would take a term, like 146 is taken here, and subtract off the term before it. And that's where it gets its name, that is a difference, and that it is common between all terms. So 150 minus 146 would have been 4. 154 minus 150, and so on and so forth. Like here we say, if I were to take one, let's say 4 minus 1, I would get 3. 7 minus 4, I get 3. Every instance of this has given me a common difference of 3, so it's going up by 3 every time. We should label this here, plus 3. This one up here was plus 4. Down here we notice that it's going down, but this is still considered to be an arithmetic thing because we could interpret this as adding on a negative 5 every time. And so our common difference here would be a negative 5, and we certainly could pick a term like 3 and subtract off the term before it to get 8 here. So one thing we want to make sure we write is this. We say the common difference is always defined as being an minus 1, or any term number minus the term right before it. So when we graph arithmetic things, as you can see over here on this graph on the left, if you had something that, say for instance, always goes up by 2 every time this goes over by 1, up by 2, over by 1, we'd be describing a situation that's very linear. And so even though we don't connect the dots with sequences, we can see that graphing the terms of arithmetic things presents a situation in which these dots are occurring in a line. So for instance, what we're seeing here is this sequence AN, and this is, as a matter of fact, this sequence that you see right here, negative 5, negative 2, 1, 4, and 7. But as we graph those with our domain values starting at 1 and going up by whole number amounts, we'd say our first term here has a value of negative 5. So we can see our first term is actually right here, and then every single time this was going up by 3, that means every time our term number goes over by 1, this is going to go up by 3. And again, this is just describing a situation where we have linear data. And the important thing is that we do not connect the dots on these. And so it's important to note that the constant term-to-term change is 3 on this graph, but the slope of the line through these points is also 3. For instance, here on this last sequence, we said it was going down by 5 every time. We could witness that the slope of the line going through these points, slope of line through points, is negative 5, and that's the same as our difference between term to term here. And so just kind of keep that in mind as we tend to look at arithmetic things. So we say that it is clear to us that the graph of each arithmetic sequence in these here forms a set of discrete points lying on a straight line. Discrete just means that there are gaps between them. It's not continuous. We say this illustrates that basically all arithmetic sequences are linear functions whose domain is just the set of positive integers. Cheers.